Hello and welcome back to this course. So last class we are looking at how to prepare these membrane electrode assemblies for low temperature polymer electrolyte membrane based fuel cells, and we saw that we have to first prepare the electrode, for which we have to coat this catalyst layer on this slurry on this electrode, and once we are done with that, we have to prepare the assembly by hot pressing this anode, cathode and electrolyte sandwich between the two. So once we do that, then the assembly is ready for us. However, for a precise coating and for better efficiency, we have to see that there are different methods that can be adopted for coating this electrode. We can go with the spray coating method, we can also go with the duct spread method, and there are few more methods that are very important and play a very vital role in enhancing this performance of this assembly. So we will go ahead and we will now start with the reaction kinetics. It can be fuel cell reaction kinetics or electrolysis in reaction kinetics, right. So for that we have to first understand the difference between electrochemical reaction and a chemical reaction. So what is an electrochemical reaction? So it's ultimately the reaction between electrode and the the species, reaction species. So we have, let me write this, it involves transfer, or rather I can say exchange of charge. So charge stands for the electrons between the electrode and the chemical species or reacting species. Whereas typical chemical reaction that also involves transfer or the exchange of charge, that is electrons, between two chemical species. Now here lies the change or difference without liberation, okay, liberation of free electrons. This is very important, and that is what differentiates the chemical and electrochemical reaction. And these free electrons, when they are liberated in electrochemical reaction, they are basically caught, and that is where we get the current. So you can say that current, let us understand a bit more about the current. So it is basically discharge, that is Q, per unit time. So what is your charge flowing in the circuit per unit time? So I can write it as dq by dt, right. So this is basically rate of transfer of charge basically. So this I, which is in coulomb per second, this I can write in terms of molar flow rate. So I can write dnf dn by dt. So dn by dt, this entire thing is in mole per second. So and dn by dt is in mole per second. Let me write it here. This is in mole per second. So however, we cannot quantify the flow rate in moles. What we can do instead, you can have a volumetric flow rate. So we have to convert this molar flow rate into volumetric flow rate. Let us do that. So it is nf times, we have to use the gas equation, ideal gas equation. So we can write P dV by dt by RT, right. So this is your volumetric flow rate. So, that is how we can also find out if we have flow rate known, we can find out the current that can be produced or rather used. So, in order to understand why we cannot have infinite amount of current flowing through this electrochemical cell. So, let us say this is our fuel cell, this is our anode and cathode, this is the electrolyte. So, anode, as we know, we have, let me write it down, at anode I have H2 giving 2H plus 2 electrons, and at cathode we have 2 moles of protons plus 2 moles of electrons plus half mole of oxygen, that gives 1 mole of water. So, as we can see, this hydrogen, when it gets oxidized, has lot of electrons on this electrode, right. So this electrode becomes relatively negative electrode, so this is a relative term, and cathode becomes positive electrode. Again, this is the relative, right. So, why are we not able to have infinite amount of current flowing through this electrochemical cell, whether it is a fuel cell, any type of fuel cell, or it can be any electrolyzer? Why we are not able to supply infinite amount of current so that we can generate infinite amount of hydrogen? So, that is in case of electrolyzer. So, answer lies, these reactions that we have seen have a finite, or they have got limitations. So, we can say that this reaction rate is finite. Now, we will understand why these reaction rates are finite in this course of study. So, let me draw this picture. So, this is our hydrogen and oxygen reaction. Let me take an example of fuel cell reaction, H2 plus half O2 giving H2O. So, this side is your free energy, and so there is some barrier that I have shown between the reactant species and product species. So, let me take an example of, let us say we have a palace, okay, palace on the top of hill. This is our palace, and we have guards that basically for the safety around the palace, and at the foothills of this the mountain, we have enemy standing here. So, if this guard wants to protect this palace from the enemies, let us say we can throw stones like this. If there has been no wall here, let us say this rate in the first place, let us say 100 stones can be thrown per unit time. However, there is a wall here, because of which this particular guard can throw only 10 stones per unit time. So, because of there is a barrier available here, so he has to lift the stones and throw all the way, crossing that barrier or a wall, due to which its speed gets affected, throwing speed gets affected. Similarly, if you want to have this reactant species converted into product species, there is some reaction barrier, and let me highlight that with a different color. This reaction barrier is between reactant species and product species, is your delta G reaction. For reactant species to be converted into product species, they have to cross this another barrier which is delta G1. So, delta G1 corresponds to the reaction barrier for the reactant species to be converted into product species. What is the case in case of product? So, this is my reaction barrier delta G2. So, this if you, in other words, if you want to convert water into the reactants, the gases, that is hydrogen and oxygen, we have to have this, overcome this delta G2 as a reaction barrier, then only water can be converted into reactant species. So, if I take this example of hydrogen oxidation, let me take the example of, so what is happening at the catalyst on the anode side, this is hydrogen. So, we have, let me show red color, so that we have a catalyst present here at the interface, right. So, this is my catalyst. Let me show this with M. M stands for the metal. What is happening is, so when this hydrogen is supplied to the electrode, anode in this case, in case of fuel cell. So, we have to again remember this, at this interface we have a triple phase boundary. So, this hydrogen which is in the bulk, it comes closer to that metal catalyst. So, this is hydrogen near electrode. So, here we have to see or understand that electrode stands for the metal catalyst, okay, or other catalyst. So, let me write this, abbreviate this near electrode as Ne. So, this stands for Ne. So, this hydrogen near electrode, once it comes in contact or once it comes closer to the catalyst nanoparticle. So, we have to see and understand with respect to the triple phase boundary, what happens, it gets chemisoft. So, M H2, okay. So, this M stands for, or let me write with the red color, this is our M, okay. So, this is our electrode surface, M stands for electrode surface. So, hydrogen when it comes in near the metal or other electrode surface, it gets chemisoft, okay. So, let me write that down. So, this reaction is basically chemisorption. So, chemisorption means this hydrogen molecule gets, it completes its or satisfies its partial bonding requirements with this metal nanoparticle, and because of which it gets chemisoft. So, it is only just literally it just goes and sits on the surface of the electrode or other metal catalyst. So, what happens next is we have this M dot H2, we have another metal nanoparticle very adjacent to this, the previous one, and that leads to chemisorption of hydrogen atoms on both of these metal nanoparticles. So, what we are trying to say is, let us say we have this triple phase boundary, and once this hydrogen which was earlier in the bulk form, when it was very far from the triple phase boundary, and when it comes near this metal nanoparticle, let us say this nanoparticle is of our interest. So, what happens is when this comes near this nanoparticle, it gets chemisoft, and we have another nanoparticle which is very adjacent, and so this shares the hydrogen atoms. So, one hydrogen atom gets chemisoft, it sits on this metal nanoparticle, the other hydrogen atom sits on the other metal nanoparticle. That is how we can see this reaction happening, M chemisoft with hydrogen chemisoft with metal nanoparticle plus one more M coming in contact, that gives 2 dot H. So, what happens next is very interesting. So, once we have this hydrogen atom chemi-soft on the one metal nanoparticle, now this is where the purpose of metal nanoparticle comes into picture. It swiftly gets this electron from the hydrogen atom, and what we are left with is proton. Again it is near electrode, okay. It is still not gone in the electrolyte, it is still very near metal nanoparticle. And since this metal or environment is highly hostile for protons, what happens is this protons that are near electrode, they get into electrolyte. So, H plus we can say bulk electrolyte. Two of such protons that are near the electrode get into the bulk electrolyte. And how does that happen? That is where your ionomer comes and plays a very vital role. So, we have this ionomer, when it was added to this catalyst slurry, it forms this pathways for the protons to basically travel from this metal interface or bulk of metal interface in the electrolyte. So, this is where your bulk of electrolyte is present, and so this becomes the interface, electrode electrolyte interface. So, if we focus our attention on the second reaction, that is M dot H, that gives M plus E plus proton near electrode. This is your slowest reaction. This is our slowest reaction, or rather step, and that is why it is called as a rate determining step. So, out of all these 5-6 reactions that we have seen, that is conversion of H2 to H plus involves so many steps, and out of that this one M dot H, that gives M plus E plus H plus near electrode, this is the slowest among all, and that is why this determines the rate of the reaction. This is also very similar to, let me take an example, that let us say we have a group of 4 friends and they are going to watch a movie, and there are only 10 minutes left, okay. They are going for a movie and there are only 10 minutes left. So, the probability of these 4 friends catching the start of the movie depends on the speed of the slowest person. So, if the slowest person is fast enough, then and then only these friends can go and catch that movie on time. So, in other words, this is what I was talking about. So, the slowest person in the group determines the speed of the entire group. Similarly, in this case, the slowest reaction determines the entire rate of the reaction, the completion of all these 5-6 reaction, and that is what this rate determining step means. So, now we will focus on the first, or rather the rate determining step. Let me quickly draw the triple phase boundary one more time. Right, and we have this hydrogen atom chemi-soft on the one metal surface, right. So, we are looking at the rate determining step again, and the purpose of this metal nanoparticle is to basically swiftly take that electron from the hydrogen and do the needful. So, how does this reaction and where are these reaction barriers come from? That is what we will see. This is our free energy. Okay. So, this is your M nanoparticle, and this is our metal interface, and this is on this side we have bulk electrolyte or electrolyte. So, this triple phase boundary, this interface is basically between the electrode and the electrolyte. So, this side onwards we can freely flow the electrons, on this side onwards we can free flow of protons. What happens here is, it's very interesting. So, let me draw like this. So, in case of hydrogen, which is chemisoft on the metal nanoparticle, so this is M chemisoft, or rather H chemisoft on M, this is 0, this is basically distance from the interface. So, in other words, this hydrogen which is chemisoft on the metal nanoparticle, it is since it has partially satisfied its bonding requirements, it is very stable with a metal interface. As and when you go away from the metal interface, its free energy increases. So, that is what has been shown here. So, this is my first sort of graph that represents the M rather H chemisoft on M. So, as we take this hydrogen away from M, its bonding requirements are going to be incomplete and its free energy will enhance. So, this is what the first graph talks about. Second graph is about the product, that is M plus E plus H plus, right, and this side on we have the electrolyte interface. So, this side is your electrolyte, this is your second reaction or second case. So, now we are concerned with the proton. So, proton, if it is highly stable in near the electrolyte. So, as we go closer to the interface, so as we move it from electrolyte side to the 0, which is the exact interface. Interface means we are bringing this proton near the metal interface or metal nanoparticles. So, since protons are not very stable in the metal interface, their free energy will also increase. So, this is how you can say the energy of the proton or the product will increase as this M plus E plus H plus, or rather in other words H plus is brought near the interface. This is my second case, and the first case talks about the hydrogen chemisoft on the metal, and as it is taken away from the interface other metal nanoparticles, its free energy will increase because it is unable to satisfy its bonds partially. So, if you look at this graphs, we can have a very clear picture of how these reactants, that is M dot H, can be converted into M plus E plus H plus, that is products. So, I can show this path of converting reactants into products. I have got this least resistance path wherein M dot H can be converted into the product, that is M plus E plus H plus, and this becomes our forward reaction and this becomes our reverse reaction. And if you look at the, you can say the reactants, let me slightly correct it. So, if you look at this reaction barriers, this is your reaction barrier for the reactant species, that is M dot H. So, once they achieve this position A, they can be converted into the products, that is M plus E plus H plus. So, this is my reaction barrier for M dot H, that is reactants. And what is my reaction barrier for the products? If I want to go from products to reactants, that is, in other words, if I want to go from go the reverse way, I need to cross this reaction barrier, that is delta G2, if you want to convert products, that is M plus E plus H plus into M dot dot H. So, in other words, if I put it in simple terms, if I want a fuel cell reaction, that is hydrogen chemisoft on metal nanoparticle to be converted into its oxidized form, that is 2 moles of protons and 2 moles of electrons. I need to basically pass this, or basically I have to cross this reaction barrier, that is delta G1, and if I want to have the reverse reaction possible, that is a reduction of hydrogen, that is 2 moles of electrons plus 2 moles of proton converting into H2, that is our reverse reaction. I need to cross this delta G2, that is the reaction barrier for the reverse reaction. And what is the reaction barrier of the complete reaction? This is the reaction barrier, that is delta G. Let me write it here, delta G reaction, right. So, what happens, let me write it down. So, this is my curve 1. So, curve 1, when my atomic hydrogen is not stable, rather it is not very stable, and its stability depends, or rather improves, I should say improves with chemisorption of atomic hydrogen to the metal electrode surface. Right. So, this chemisorption to the metal surface allows hydrogen basically to partially satisfy its bonding requirements and therefore lowering its free energy So, basically if we take it away from the metal interface, its free energy will increase. So, chemisoft hydrogen will always be stable with the metal interface. What is happening with our second curve? Let me write that. So, curve second, so let me write it, free energy of protons in the electrolyte working against the repulsive forces between charge ion and the metal surface. Therefore, the energy increases as proton is brought closer to metal surface. This is important, and because it is energetically unfavorable for proton to exist in metal phase, this free energy of proton is lowest in or lowest when it is deep within the electrolyte. In other words, far from the metal surface or metal interface. And what is this A? That one that we have written here. This A stands for the activated state. So let me write it here. This A is basically activated space, activated state. So what is the significance of this activated state? Only those species that basically achieve this activated state can be converted into product species, or vice versa. Only product species that can achieve this activated state can be converted into the reactant species. So let me write that down. So species in activated state, so they have to overcome the energy barrier, which is applicable with the both of the species, whether it's a reactant species or the product species. They have to overcome this energy barrier, and after that only they can be converted into product. That is, reactant species can be converted into products and vice versa. So that is the significance of activated state. Not all these species can achieve this activated state. So those who achieve can be converted into product space, and that is one of the reasons why the reaction rate is finite, and that is one of the reasons we get very limited current or finite current in the case of fuel cells. So we will stop here and we will look at more into this reaction kinetics in the upcoming classes. Thank you.